Buenas tardes, Gabriela. What I promised to do today is touch on binomial a bit, and then we'll get into the sampling distribution of a statistics. Hi, Valeria. I asked you to watch some of those videos in the sampling distribution. That'll just make my job easier today. So in the notes, I use this example to generate the formula for the binomial. And we already saw this example, and we already saw the probability distribution of flipping 4 coins and their outcome. Actually, X is the number of tails observed in 4 flips. So we described it, and then I proved, or I derived the formula using this as an example. And I explained that we needed to know the number of ways of seeing 2 tails out of 4 flips. So it turns out there are 6 ways if you list them, but let's say your n was 1,000. It wouldn't be clear how many possibilities there are, so we have to use what's known as a combination calculation. In this example, n is 4, and I want to know about k equals 2. That's what's interesting to me. So I would calculate 4 choose 2, and I showed you how to get it on your calculator. 4 choose 2 is actually calculated with factorials, and this is the result of probability. These were developed for calculating probabilities. In this particular case, this demonstrates the number of ways of seeing 2 successes out of 4 trials. So factorial means 4 factorial means 4 times 3 times 2 times 1. In general, n factorial means n times n minus 1 all the way to 1. And we don't have to use that because we have our calculator, but that's actually the calculation you need to make. And it's just accounting for all the different combinations or representations of, in this case, 2 tails in 4 flips of a coin. So then I explain that generates this formula, and then I apply it, and we pretty much did this in class. So what is the k? The k is the x of interest, where x could be any of 0, 1, 2, all the way to n. And we also saw last class that if we want more than just one of these, we can add the probabilities together. So we apply the formula several times. This generates the probability distribution here, and then we can use it to answer questions about what to expect. I just wanted to speak a moment about the binomial coefficient, and this is all in the notes. I'm just explaining why we use that formula. And if you got it from yesterday, you don't have to worry too much. You can read that through very easily. So the binomial coefficient, it turns out that it is symmetric. You see, this goes 1, 6, and then it's 1, 6 on this side. Then 15 and 20 in the middle. I probably need to close my window. It's just pretty hot in here. Hold on. Maybe that'll be more quiet. Okay. So the binomial coefficient turns out to be symmetric, but the probability distribution isn't necessarily symmetric. It is here. And it works out that way that it's symmetric because of the way the formula is. If p is equal to 0.5, the distribution will be symmetric. All right? Because all you're doing, if you think of the formula, if it's always 0.5 and 0.5, then you can be sure that on this side, let's go back here. You can be sure that because these don't change, they're always 0.5, as you go through and cycle through all the different exponents, so 0, n, 1, n minus 1, all the way to n 0, these values will be the same symmetrically. So it'll look symmetric. If it's not 0.5, it's not going to be symmetric. So we're going to have a look at that in a moment. I want to emphasize then, we talked about this and this case, 620 and 626 are always 1, right? Because how many ways of seeing no successes in 6? Well, failure, 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 6 failures. There's only one way to see that. That's why it's 1. And how many ways are there of seeing 6 successes out of 6 tries? Well, that's success, 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 success. So that's only one way. And then these two are each going to be 6 for the same reason. Oh, we saw that in class. The other ones aren't so clear, so you would probably have to use your calculator. But the binomial coefficient has perfect symmetry always. The thing that will make the binomial distribution unsymmetric or non-symmetric or asymmetric will be the value of p. In fact, symmetry of the binomial distribution actually depends on p being 0.5 or a relationship between n and p that we're going to discuss soon. A relationship between n and p to be discussed. So what I wanted to do was show you how to do this in Excel. We're going to generate a probability distribution in Excel. And before Excel, statisticians just use tables to get their answers. So you can actually find tables online to make these calculations. So you could calculate all these. Here's an example of a table. So here, books and books of tables, or books of tables and tables, are available in digital form. You could probably get physical ones too. And you see for any n and a p, you can get the distribution. So if p is 0.05, this is the distribution. Now the distribution is cumulative. It means that it's adding up as you go along. So this one includes just x equals 0, but this one includes x equals 0 or x equals 1, so it adds them together. And this one is px equals 0 or x equals 1 or x equals 2. So it's cumulative. So in the end, you always get 1. Now n is 15 here, but it becomes 1% pretty soon because these are going to be very small values. So you could generate that in Excel if you want. We can try that. Here's the code. If you want cumulative values, you need to tell Excel the K that you want, the N that you want, the P that you want, and then cumulative would be 1. If you don't want it to be cumulative, you say false, 0, so that it will give you the values like we were calculating them here. So you get them separate. Okay, just one at a time. So let's see if we can do that. Let's go to Excel. If I say equals binomial distribution, it asks me for which one I want. So let's say I want 0 successes in 15 trials and the probability is 0.05. And I say cumulative, no. So that's the first value. Let's see if that's true, 0.4632. If I go back to the notes where we had that table, where's that table? You see? This is the one I calculated. 0.4633 they got here, and I got 4633 as well if I round it. So this is for n equals n equals 15 and p equals 0.05. So this is for n of 1. No, sorry, n of 0. That is for x equals 0 or k equals 0. Now if you want to do this for the next one, you can copy and then just change this value, not that value, this value to 1. So that's the next one. Then the next value changed to 2. All right. So what this is doing, this is not cumulative, it's going one at a time. But if I accumulate them, So this is adding as I'm going up, around, along. This is cumulative. And so that's how you can generate the binomial distribution. If I actually put 1, 2, 3, let's see if I can put the whole thing. If I put 1, 2, 3, 4, 5, and I actually put here, I actually put this cell, that will work better. So then when I copy this, it should, yes, okay. All right, so now it's using whatever I put here. So I can go all the way to 15. No, that didn't work. You see how small they get. So this is clearly not symmetric, right? It's just getting smaller and smaller and smaller. And I can copy that formula all the way down. You see how we're rapidly approaching one like the table does. So I've generated using that table using Excel. If instead of using a 0 at the end, I use a 1, I would get the table here. This is cumulative. So these numbers 4, 6, 3, actually let's copy them. And take them back so I don't have to. So let's compare what we got with what's here in the table. So 4, 6, 3, 2 is the first one, then 8, 2, 9, 0, 5. Okay, so this doesn't round the same, but 9, 6, 3, 8, 9, 9, 4, 5. You see? It's replicating. So we pretty much made that table. Any questions about this? So you can do this with Excel, you can use the long formula, you can use tables. And in fact, tables were what was used in the 60s and 70s, even the 80s. When I studied statistics, we got a book of tables in the 90s. So I still teach you with the tables for this standard normal, but not for binomial. But you should know they exist. All right. So then I have a bunch of problems for you to practice. Please let me know if you have any questions about those problems. I think that's all I want to say about the binomial, unless you have questions. There are a ton of problems to practice with. No questions? So I'm going to start here. regarding the sampling distribution of a statistic. However, I want to show you what I'm going to use to teach you over the next 3 days. I'm going to reference this formula sheet at the end of Unit 5. It has all the formulas you need for the final exam. This is the formula we just discussed, the binomial formula, and you have an idea where it comes from and how to use it. So K can be 0 through n, and this will give you the value each time. And depending on the question, you might want to solve this for many different K and sum them together. So this is known, X is known as the count variable. And this number 1 tells you about it summarizes the unit on binomial, and it actually does explain or summarize the notes for sampling distribution of the statistic X. X is a statistic. Why is X a statistic? What is X again? X is the number of successes in an independent trials. In other words, it's a count, so it's a number computed from a sample. So X is a statistic. We call it the count variable. And as a statistic, it's actually a statistic is actually a variable, because the statistic that we calculate is dependent on the sample, but we could have had other samples. It didn't have to be the one that we got. So our statistic could have been a range of things, a number of things. So where it comes from is its distribution. So X, I say here, X has a binomial distribution with parameters n and p. Then X has a mean np and standard deviation np, 1 minus p square root. Where in the world am I getting all that from? Wasn't this just a calculation of X? Well, the fact is X is binomial n and p with mean so I use this notation np and standard deviation np 1 minus p square root. So where in the world am I getting this from? That's what we're going to talk about next. So I want you to keep this, I want you to print this out and keep it nearby for the next 5 days, until the test. Wednesday, Thursday, Friday, Saturday, Sunday, Monday, like 6 days. So where does this come from? Let's go back to the notes. imagine that a basketball player makes 800% of her free throws. The mean number made in 10 tries should be 80%. So how did I get that? Well, I took 10, multiplied it by the chance that she makes it in, and I get 8. So all I've done is taken n, which is the 10, times p, which is the probability of a success, and I got 80%. So this n times p is actually the expected value or the mean. Now this is understanding, this is logical, but you can actually solve for that theoretically, and I describe it here how I would get that. This is a matter of understanding or applying the rules of means and variances to this concept of taking each trial in turn, each independent trial, and adding the outcomes. So here I define each trial as the Bernoulli random variable, indicating success, so that the probability distribution has the outcome no or yes. It was not a success or it was a success. So the chance of success is p, the chance of failure is 1 minus p, so we know that. Using this distribution, we can calculate the mean and the variance of a Bernoulli trial or Bernoulli random variable. And we get that the mean is p, and the variance after this long exposition that's not hard to follow is p1 minus p. Now using that and putting that together in the binomial problem is repeat this n times. So repeating this n times means I'm going to add together, I'm going to create this count variable, adding together the outcomes of those n trials. Then using the rules of means and variances, the expected value of a sum of variables is just the sum of the means. So that's where the n times p comes from. In terms of variances, I'm going to do the same thing. The variance of a sum of random variables is the variance of the sum, remember when they're independent. Since the trials are independent, we can do this. There's no extra covariance term. So it's just the variances, and the variances, what we figured out here were p times 1 minus p. So that's just n of those. So that is the variance. That means that the standard deviation is the square root of that. So by theory, I get these results. You guys can look at that. You'll feel really great if you understand it. I'm not going to ask you to prove any of that, but it just reinforces that this is where it comes from. We're applying, and then why I taught you those rules, so that you can understand the theory behind what we're doing. The intuition is there for the mean, but it's not so much there for the variance or standard deviation. So what does this look like? Let's say we have a binomially distributed variable with an n of 5 and a p of 0.4. I could find the whole probability distribution. I could use Excel to get it all filled in here. Oh, this one should be up there. It got bumped. And Actually, I could probably take it with me. Okay. And I could graph it. Now looking at this graph, where is the mean? Where is the balancing point of the distribution? Very good. So it looks like the balancing point is at 2. And that's not a coincidence that n times p, remember that's from here, x was binomial 5, 0.4. So the mean of x, I told you, should be n times p. What is n? 5. And what is p? 0.4. So it turns out to be 2. So it's not just visually clear, you can actually calculate it. All right, so what about the standard deviation? The standard deviation would be np 1 minus p square root. So we can plug that in. N is 5, p is 0.4, and 1 minus p is 0.6 square root. So when you get that all together, it's 1.095. So looking at this, this is not perfectly symmetric, but I could calculate the mean and the standard deviation for it in general. Okay, so that is true about the variable x, which is a statistic. It comes from a distribution, and I know its mean and standard deviation. Okay? So this is your first introduction to sampling distributions of a statistic. What I want to talk about next is when would we expect to see that this is symmetric? It's very important because if we can assume that x is normally distributed, we can answer questions about what to expect using the normal distribution instead. Now that would be easier in cases where you have a very large n. Let's say you had, n equals, let's just say like 1,000 or even 100. Let's say n was 100 and you wanted to know, so let's say that ESP example. Remember the ESP example? So an individual would be asked to look at or to guess without looking, obviously, at the shape on a card by reading the experimenter's or the research assistant's mind. And they would be judged to have ESP if they guessed at least 50 correctly. So what's the probability that they guess at least 50 correctly, where X is the number of correct guesses? So to answer this question, we would have to calculate the probability X equals 50 plus the probability X equals 51 plus the probability X equals 52. And you know, it wouldn't be easy unless we did have software, you know, or a table of values. So we'd have to calculate all of those to 100. So statisticians found an easier way to deal with that kind of question. What they did was find circumstances where we could use a normal approximation to the binomial. So we begin by asking, when would the binomial distribution be symmetric? We know that it'll be symmetric if p equals 0.5. I already explained why, and if you didn't get it, just look at the formula, you'll see why that's the case. The binomial coefficient is symmetric, so as long as p is 0.5, the other part of the formula will also be symmetric, and it'll make it symmetric. So here, for instance, the p was not 0.5, and it's not exactly symmetric. It's a little bit off. But it will be symmetric in a special case. And that case is, it turns out, when n times p is greater than or equal to 10, and n times 1 minus p is greater than or equal to 10. In that case, we can take the mean and standard deviation as though they are the mean and standard deviation of a normal distribution that approximates x. So in the symbols here, I have put this double tilde sign. That means approximates. Well, we did talk about that before. So let's see. For instance, this all begins around with a p of 0.5. We expect to have symmetry, but what about normality? That's different than symmetry, right? We discussed that. There's a very specific characteristic of normal distributions, right? It's 68, 95, 99.7%. That rule. So this is not just symmetric. This is going to be normal, approximately. So for n times p greater than or equal to 10, it's true because n is 20 and p is 0.5, and that's exactly 10. And what about n times 1 minus p? N times 1 minus p is 20 times 0.5 as well. So that's equal 10, and so that's greater than or equal to 20. So it satisfies our criteria, and so we can imagine that this binomial distribution, I need a thicker one. Is what? it's approximately actually I'm going to write it the long way. So x distributed binomial with a with a n of 20 and a p of 0.5 implies that x is approximately normal with a mean of np, which is 10, and a standard deviation of np 1 minus p square root, which is 2.24. And this is true because we did a check. N times p is greater than or equal to 10, and n times 1 minus p is greater than or equal to 10. Now, I'm not going to go into the proof of why that makes it so. You just need to know it. There's some things I have to leave out. Okay? And then, if I have any questions about what to expect, x is greater than this, x is greater than that, however, whatever it is I'm looking at, I will now use the normal distribution. So this is why I explained to you that the normal distribution is very important for this course. We're going to be using it until the end. All right, so let's look at what we can do with this. Given x has a binomial distribution such as with n equals 100 and p equals 1/3, find the probability that x is greater than 23. So in normal situation, we would have to we'd have to find x equals 24 and add it to the chance that x equals 25 all the way to x equals 100. Or we could have done this backwards, but whatever. We could have done it like 1 minus probability x equals 0 plus, don't ever forget the 0, x equals 1 all the way to x equals 23. But still, it's a lot to calculate, right? If you have Excel, it's not so bad, but without Excel, it's a lot to work on. So instead, we're going to use, and theoretically too, it's good to have this approximation. So Let's check if we can use it. Step 1 is to check that n times p is greater than or equal to 10. It is. It is. And then n times 1 minus p is greater than or equal to 10, and it is. So then we can say that x is approximately normal with a mean np and a standard deviation np1 minus p square root. So we calculate them and we use them to answer the question, just as though this was a normal distribution problem. We standardize and get the answer. Any questions? I'm not going to write this down. You can sit and go through the steps, but it's we spent time learning the normal distribution, so I won't have to do that again. But you should be able to verify these answers using your table or Excel. The thing I need you to learn today is step 1 and 2. Let's see another example. Let's look at the ESP one finally. Let's answer that question. For the ESP example, n is 100 and p is 0.25. And we want to find the probability that x is greater than or equal to 50. So first we perform this check. Let's check that n times p is greater than or equal to 10, and it is. And that n times 1 minus p is greater than or equal to 10, and it is. So that means that x is approximately normal with a mean of np and a standard deviation np1 minus p square root. So when you calculate those, these are the values you get. Now let's answer the question. What's the chance that x is greater than or equal to 50 correct guesses? It's going to be very small because it's unlikely that someone will be found to have ESP, but let's take x and standardize it with the new mean and the new standard deviation. Like, this notation is just to remind you, like with the subscripts, that we created a new variable. You don't have to write with this notation every time, I don't mind, as long as you know to standardize. Minus 25 divided by 4.33, and we know that if I draw this, try that again. You know, 5.77 is way over here, and there's nothing there really. So the chance is 0, as I suspected. So in conclusion, regarding the ESP example, it's highly unlikely, it's virtually impossible for a person who is just guessing to be found to have ESP. So these are the types of things you can do. These are the types of things you can do with this new property. Okay, and so number 1, I say everything that we've been using, and then x is approximately normally distributed provided np is greater than or equal to 10 and n times 1 minus p is greater than or equal to 10. And I mentioned that the population size is large. This is another criteria that is required for the theory to work. So usually if it's not stated, you assume it. Like, notice I don't talk much about the population. That's an assumption that the population is large for this to be true, for all of these results to be true. So this is what you use when it's not the case. You have to count one by one, and if it is the case, then you use the properties given here that x is approximately normal with a mean of NP and a standard deviation NP1 minus P to make estimations. Okay, now we're going to move into number 2. So we're done with 1. We're going to move into number 2, get to number 3 today, and be halfway home. All right, so maybe it might be the case, and it's most likely the case, that people don't want to talk about how many successes there are. They're probably going to want to refer to the proportion of successes. So I'm going to define a new statistic called sample proportion. And it's made up of x, the number of successes in n trials, divided by n, the total number of trials. So because of the rules of means and variances, this new statistic, this new variable, is made up of a variable we know about. So we should be able to compute its mean and standard deviation. So let's see, what should be the mean of this new variable? What should be the standard deviation? If it turns out that n times p is greater than or equal to 10, and n times 1 minus p is greater than or equal to 10, then the sample proportion is also approximately normal. But I'm going to use the notation here that we have to find the mean of p hat and the standard deviation of p hat. And it turns out that the expected value of p hat is the true proportion. So what we're saying is that the sample proportion of successes on average in repeated sampling should have the expected value of the true proportion. So that's neat, isn't it? Right? This will show us, this demonstrates that the one sample that we take and the proportion we calculate from it, the proportion of successes, comes from a distribution where the expected value is the true proportion. So we're going to use that fact when we don't know the true proportion. Okay, that's what we're going to use this for. But right now we're building the theory. So it turns out that this should be the expected value, and this should be the standard deviation. So where do these come from? Well, they look familiar. We get them from what we know about x. Remember, x has mean NP and standard deviation NP1 minus p. All we have to do, just like we divided x by n, whatever we do to the random variable, we do to the mean. So I get to divide NP by n. And remember, anything that I do to the random variable, I can also do to the variance, provided that, or the standard deviation, provided that well, in this case it's just 1, so I can just do it to the standard deviation. So I'm dividing through by n for the mean, I'm dividing through by n for the standard deviation. Okay? So remember that rule we had so whatever I do to x, I also do to the standard deviation. So I multiply b by x, but not the a part. The a part drops out because the shift doesn't affect the spread of the distribution. So if I'm talking about the variance, I have to square it. But if I'm talking about the standard deviation, it's just the b. So that's what's happening here. It's not b. I'm actually multiplying by 1 over n, or dividing by n. So what happens is I simplify this. If I divide this by n, I can put this amount into the root sign. That's what I do here, and then cancel. One of these cancels with the n on top, and that leaves that. So this is the distribution of p hat. This is the sampling distribution of this statistic sample proportion. So what do we do with this? Well, we're going to replicate our answers, but now answering for the proportion, the sample proportion. Now our answer should be identical, shouldn't change. It's just looking at it from a different perspective, talking about proportion as opposed to talking about the count. Above, you are asked to find the probability that x is greater than 23. 23 out of 100, right? There were 100 trials. So what proportion is 23 out of 100? So instead of answering the question x greater than 23, I can answer the question p hat greater than 0.23. That's the same question. So I should get the same answer. The difference is I'm going to use the mean and standard deviation of p hat now. So I have to calculate them. So conducting my step, I already know that n times p is greater than 10 and n times 1 minus p is greater than 10. So it's the same as above when I did this problem. But now we need to calculate p and, the mean and standard deviation of p hat. Now from the formula, or from what we learned, let me grab that from here. I want to use this property, so I'll make it bigger. So where the sampling proportion is just x over n, the mean, it will be approximately normal with a mean of p. So p was 1/3, so that's just p. And the standard deviation is p, 1 minus p over n, with a square root around it. So that's this. So now I have the mean and the standard deviation. To solve the problem, I standardize, and I get the same answer as I did before. Questions? right, now let's answer the other question on the ESP for this using the sampling distribution, sample proportion. So using the sample proportion, rather than greater than or equal to 50, 50 out of 100 is 50%, right? So we're going to check that the proportion, sample proportion, is greater than or equal to 50 or 0.5. So all we have to do, we know first of all that the step 1 check to make sure we can do this is true. N times p is greater than 10, and n times 1 minus p was greater than 10. We already checked that before. Now let's find the new mean and standard deviation for this p hat. The mean is just p, and the standard deviation is calculated as 0.0433. So now I can use it to calculate, to standardize, and I get the same answer as above. So again, the thing you need to learn here are calculating the mean and standard deviation of these otherwise binomial variables. So I have some other exercises for you to try. Verify the remaining ones on your own. Okay? Because I'm just going to be annoyingly reading the notes, and you need to practice. Make more time, make the best of these questions if you do them yourself. So there's some questions, and that is that. Brings me to page 25. So let me, before I go to page 25, let me show you what we've done so far. So we've done number 1. Number 2 is all SDS on p hat. Given that x has a binomial distribution n and p, the sampling distribution of p hat, the sample proportion, I'll write it down here, is x over n. It has a mean of p and a standard deviation of p, 1 minus p over n, square root. And x is also approximately normally distributed provided n times p is greater than or equal to 10 and n times 1 minus p is greater than or equal to 10 and the population size is large. I just repeated that. Okay, so practice answering those types of questions. So I taught you how, sorry, I need to turn that off. Sorry about that. Okay, so the results that we've been calculating with the normal distribution are all approximations. Keep in mind the binomial distributions are discrete while normal distributions are continuous. If you'd like to be more exact, more precise, or as close as possible to the binomial equivalent, you can use the continuity correction factor approach. So what that involves is taking stock of the fact that the binomial distribution is just the spiked drawing, but to get the normal distribution, we need to fill it in here. And when we do that, we're losing account of the fact that the entire spike here would refer to 15. I mean, the entire box around the spike should be 15. And here the entire spike around, the entire rectangle around the spike at 14 should be 14. So how do we correct for that to get more precise calculation of probability? One moment. Sorry, I recently got contacts and I have to remember not to touch my eyes because I move them around. All right. So what we're going to do is make adjustments. Let's say that we want the probability. Let's refer to the ones that we already did, like x greater than 23. So if x is greater than 23, it means that I want to account for the 23 density all as one and calculate after 24, like with the 24 bar after the 23rd. So to account for that in the continuous distribution that the normal distribution is, I need to make an adjustment called the continuity correction factor. And where I want to start is really 23.5 because we've added density around each spike of 0.5 on either side. So when I do that, I improve the approximation. So you would proceed as usual, but standardized 23.5 instead of 23. So what I've just described is this case here. I mean, I could write greater than or equals to, but it doesn't matter because it's a continuous distribution now, but that's what it would be. So what if it was x, I wanted x less than 23? What would be the correction factor for that? For x to be less than 23, I don't want to include 23. I want to include everything below 23. So I'd start at 22.5. And that is case, that one. So I have to go less by 0.5. Are you following me? What if we wanted x, what about at 23? We can't even do this in the normal distribution, can we? Because it's an equals. So how do we fix that? How do we make an account for that? Well, in this case, the continuity correction requires us to go on both sides to get this whole spike, the bar around the entire spike. So what do? We correct x in the middle, x greater than 22.5 and less than, and I can put equals, and less than 23.5. So I have to give a little bit on each side to answer that question. That's an example of that. And let's do the last two with another drawing. So what if we want the probability that x is less than or equal to 23? What would be the correction factor there? Less than or equal to 23 would involve the 23rd bar and everything below it. So we would have to change this question into x less than or equal to 23.5. And finally, so that's this one here. And we have one more to do. What about x greater than or equal to 23? That would be all of this. So I'd have to go backwards. Greater than or equal to 22.5 to include the 23rd bar. All right, so this is the adjustment that will make your result not an approximation, but sometimes I use the word exact as opposed to an approximation. So you can still use the normal distribution as an approximation, but this improves your approximation. And it corrects for the fact that you've gone from a discrete distribution to a continuous distribution. And it's an interesting technique, and it's important when you're reading statistics to understand what is it they're talking about. So you got the hang of it? I did so many there. So review this video if it's not clear, and I think I have another one for you as well about it. Okay, so you got the hang of that? And then I do some extra exercises you can practice, so you can verify looking at those exercises. So from here on out, I give you all the answers, right? Most of my notes have the answers to the questions I pose anyway. So you can check your work. So you can check all of that and do all these problems and try all of these. And that brings us here. Page 33. Or actually, I think I don't know. It's page 31. But I guess because I have extra pages I generated. Not sure. So we are now on number 3. Now I didn't write anything about the continuity correction factor here. You can make a note to yourself if you want to use this formula sheet as a summary of the course for the final. You can make a note about the continuity correction factor in there. So we're at number 3. So we've spent time talking about the sampling distribution of the sample count. We talked about the sample proportion, and now we're going to talk about the sample mean. The sampling distribution of the statistic x bar is what we're going to focus on next. If x has a mean of mu and a standard deviation of sigma, the sampling distribution of x bar has a mean of mu and a standard deviation of sigma over root n. And it also has a normal shape, provided that the original x was normally distributed, or if you don't know the distribution of the original variable of the population that it comes from, then as long as the sample size is large enough, and we'll use 25, you can say that it's approximately normally distributed. So what am I talking about? I'm talking about this. So if we're drawing a sample from a population, let's call that sample simple random sample. And here are the outcomes, x1, x2, up to xn. From that sample, we can calculate statistic x bar. Let's go back to the population and sample again. Okay, put back all those ones that you selected, put them back, and get a second sample. The second sample results could be x1. We'll name them x1 star because it's not necessarily the same as the original one. x2 star and up to xn star. And we could calculate a different sample mean. So if I did this repeated samples, so think about all possible samples. And I put my findings into an Excel spreadsheet. What do you expect? What would you know about these sample means? Well, the one that you got, let's say this was the one that you got, that one comes from a distribution of several. And what do you know about that distribution? In particular, what is the average of those sample means? And then what is the standard deviation of those sample means? Presumably we're doing this because the original population, was symmetric of some kind. But let's say that we knew that the original population was normally distributed with a mean of mu and a standard deviation of sigma. Let's say we knew that. Then what do we expect about the distribution of x bar? Will the frequency histogram that we draw with this data here also have the same shape, the same mean, and the same standard deviation, or will it be different? The truth is that you're going to witness the law of averages, that these averages will also have the same overall average as all the values do, all possible values. So it will have the same mean, should have the same mean. However, they won't be as spread out as the original values because each of them are going to be closer to the mean than the overall, like all of the numbers. So because they're closer to the overall mean, mu, then that means they're closer together. So that will make their variance or standard deviation smaller. And it turns out if you start with a normal distribution, they are going to be closer by a factor of 1/n. So those will be the mean and standard deviation, and it turns out that the shape should also have that normal appearance, right? That predictable appearance. If you start with a normal, you get a normal in the distribution of all the sample means. And you get the same mean, but it's going to be a tighter distribution. So that's what my image is supposed to be here. These are tighter together, closer to the true mean than the original values. And this has to have a bar on it. Okay, so this is the sampling distribution of x bar. The x bar we get comes from a sample of a number of possible means. So what if we don't know that the distribution is normal? What then? If we don't know the distribution is normal, if we don't know anything about the mean and standard deviation of the distribution, x bar will be approximately normal with a mean of mu and a standard deviation that's smaller by a factor of 1 over n. Provided that your sample size is large enough. So it doesn't matter that you started with a normally distributed variable to know something about its sampling distribution. As long as the sample size is large enough. So I describe in a video this result here. So make sure you watch this video. I'm not going to do it now because it does take some time. So make sure you watch this. And what it describes is the central limit theorem that I just outlined. If I ever ask you or someone asks you for the central limit theorem, it is this result here. That we don't need to know the shape of the distribution of the characteristic of interest. Provided the sample size is large enough, we can assume that the sample mean is normal with the mean and a smaller standard deviation by a factor of 1 over n. That's a huge result. That makes it possible for us to do so many things with samples and make predictions about what to expect in those samples, which is also very important. So the important results are that the shape of the sampling distribution is normal if the random variable x is normal. That's the first one. Important result number 2, that the mean of the sampling distribution is the true mean. This captures the idea that our estimate x bar is an unbiased estimator of the parameter mu, because on average that x bar comes from a distribution that has the true mean as its expected value. That's known as an unbiased estimator. The third result is regards to the standard error This idea that the standard error, the new one, is sigma over square root of n has a special property that we can exploit. In fact, it depends on something we choose. We don't choose the variation of the variable. That's a given. Whatever the variable is, its characteristic, its parameter, the standard deviation, cannot be affected by us. But what can be affected is our sample size. So we can choose n in such a way to get a standard deviation that we like of our sample mean. So that's quite powerful. So how can we use that? Let's say we want to get a smaller, so why would we want to get a smaller standard deviation? Because it would mean that our estimate is closer to the true mean, right? With a standard deviation that's small, it means that you are closer to the actual mean. So let's say we start with So what sample size would you require to reduce your standard deviation by half? So if you want to reduce the standard deviation of x bar to 1/2 of what it is, what sample size will you require? So let's say you have, this is the standard deviation of x bar. And you want 1/2 of that. What would that mean? So you see, to get half of this amount is the same as using a sample size times 4. What if you want to go to much smaller, even 1/10 of what it is? Then when you would say 1/10 of this should be written like that, or so you would have to multiply your sample size by 100 to reduce the standard deviation to 1/10 of what it is. So because of that, because of the way the new standard deviation, the standard deviation of x bar works, we have a simple rule that you need to follow. In this box. It can be seen that by reducing the standard deviation of the sample mean to 1/k of its original value, we require k squared times the sample size. So if we want to go by 2, 1/2, so that's how you use that rule. So 1/2 means that k is 2. So k squared is 4 times the sample size, and this is why. One-tenth means k is 10. So k squared is 10 squared, which is 100 times the sample size. And it's all because of that square root sign. To get into here, you have to square the result, or the k. Okay? That's how the square root sign affects things. All right, so now let's use this property. Let's apply this. I prove it here, and I'm not going to test you on this, but I prove those results that the mean of x bar is going to be mu, and the standard deviation of x bar is going to be sigma over root n. I actually prove it using the rules of means and variances. All right, so let's apply this, and then you guys can work with trying to understand what I just talked about. Let's apply this to some questions. Doesn't my screen look dark? Why does it look dark? Let's see what happened to my lighting. I don't know, it looked dark to me. Okay. All right, so you have all the answers to these, but let's do a few of these together, okay? Let x be a variable on some large population. So x is known to be normally distributed with mean 13.8. So notice I say this large. You're going to see that because you need that assumption. X is normal with a mean of 13.8 and a standard deviation of 2.9. With a sample of size 9, the sample mean will also have a distribution that's normal with a mean that is the same, but a standard deviation that's smaller because the sample means are closer together than the original values. So that would be sigma over root n, sigma over square root of 9. Which is 0.967. So my original values have 1 decimal place, so I'm going to keep 2 extra. That's my rule. So the question was, state the distribution of the variable x bar include the name and the relevant parameters. So I've done that. So I use the first part of the results I mentioned because I know that X is normally distributed. I can say that X bar is also normally distributed regardless of the sample size. And now I can make predictions about what to expect in my sample. Find the probability that X bar is larger than 15. So find the probability that X bar is greater than 15 means that I can just, because X bar is normally distributed, I can just standardize that. Turn this into a Z, subtracting 13.8 and dividing by 0.967, get my answer. .24. So the chance is 1.24 standard deviations. Sorry, I didn't want to do that. You want the chance that we are 1.24 standard deviations above the mean. So looking that up, on the positive table, if I go to 1.24, it's going to give me the left side, right? So 1.24 is this here. 0.8925. Sorry. So 0.8925 on the right side would be 10.75 on the right side. So the answer is 10%, 10.75% chance that X bar is larger than 15. Notice that 15 is quite close to 13.8. But the standard deviation is so low. That it's a very tight distribution. So this turns out to be 1.24 standard deviations away, and that only leaves 10% chance that it'll be larger. All right, so let's see what's next. Let me give you a moment. You guys can use that as an example and try this next one if you haven't already. Try this next problem. I'll give you 5 minutes. Okay, I'm back. So how'd you do on this one? Did you just look at the answer or did you try it? So the weight of the egg produced by a certain breed of hen is normally distributed. The weight of the eggs. So X is weight of an egg. Notice I'm using X now as a normally distributed thing, right? So X is normal with mean 65 and standard deviation 5. Think of cartons of such eggs as a simple random sample of 12. So if I take 12, then I want to know about the average egg in a carton. Should also be normally, the average weight of an egg in a carton should be normally distributed with a mean of 65 and a standard deviation of sigma over root n, 5 divided by square root of 12. So this is 1.44. So if I want to know about what's the probability that the weight of a carton these are the carton weights. But I want to know about the egg in the carton. So I have to adjust those before I continue. I have to talk about not 750 but 62.5 as the egg. And 825 divided by 12 is 68.75. Okay, because X bar is the average weight of an egg in a carton of 12. So you got to be careful that you're answering the question in terms of the right variable. If you use 750 and 825, that's about the whole carton, but you don't have information on the carton weights. You have information on the average weight of an egg in the carton. So you have to adjust the question to match your distribution. So now we standardize. So this is negative 1.74 and this is 2.60. Are you guys still with me? Are you getting my numbers? All right, so then you guys can check the rest of the answers here. So using the normal distribution, the answer should be 95.44%. So you verify that, okay? So the trick was that you needed to adjust these to refer to the average egg in the carton, not the carton weight. I want to do I'm going to ask you to try this one yourself. The answer is there. You can let me know if you need help, but I really want to do the last one. I really want to work on the fourth one. So let me give you 5 minutes to try this one without looking at the answer, and then I'll help you with it. All right, so how many people are in a car? A study of rush hour traffic in San Francisco counts the number of people in each car entering a freeway at a suburban interchange. Suppose that this count has a mean of 1.5 and standard deviation of 0.7. In the population of all cars that enter at this interchange. So what we're saying is X is, well, we don't know the distribution, but it has a mean of 1.5 and a standard deviation of 0.75. But we don't know the distribution. The question here is, could the count be normal? Well, count variables are discrete. They're not continuous like a normal distribution. Okay, so that's the answer there. Traffic engineers estimate that the capacity of the interchange is 700 cars per hour. According to the central limit theorem, what is the approximate distribution of the mean number of persons, x bar, in 700 randomly selected cars at the interchange? So what I'm saying is, we know that x has a mean of 1.5 and a standard deviation of 0.75. If we take a sample of 700, then x bar is approximately normal with the same mean and a standard deviation that's smaller in approximation, and that would be the result there. So that's what the central limit theorem tells us. Even though we don't know the distribution of the variable, in this case the number of people in a car, we know that the sample mean, the mean number of people in a car, is going to have a mean of 1.5 and a standard deviation of 0.75 divided by 700 square root, which is 0.028. So this is where I get to use the central limit theorem, and then use it to calculate or approximate the number of people in 700 cars. Now notice, this is the number of people total, but this information is about the average number of people in a car. So again, like I did before for the problem about the cartons of eggs, I have to adjust that to be an average number, not the total. This is the total. I mean, I don't think I had to do it that. I think I just used 1.5 in the notes, because the original numbers, anyway, on average, it's 1.5 people in a car. So what I want to calculate is the probability that x bar is greater than 1.5 using the information I have, I can find how many standard deviations that is, and it's really z is greater than 0, isn't it? Let me make sure I did that in the solutions so I don't confuse you. I used 2 digits. Okay, let's just do it that way. So I rounded this to 5-4, and this is the question I answered. So we have a little bit of work to do. It's not so easy. So then it's standardizing 1.54 minus 1.5 divided by 0.028 is z greater than 1.43. And then using the normal table, I have a different answer here. No, 1.41. Why do I have 1.4? Did I do something wrong? Let's just do this. 0.028. Did I have a different number? 283. Okay, I used 4 decimal places. So I used 4 decimal places here, and then that put that there, and then that made that 41. You should be using 2 more decimal places than the original numbers. I guess that's right, because I had 2 decimal places here. So yeah, I should keep 4. So then this makes it 41, just slightly different. So that's how you're going to get my answers. Keep sticking with that rule as best you can. And then when you look it up in the table, you get that you can look up, to make this faster, you can look up, change the sign and the direction, and you can look on the negative table for 1.41 and get the answer. So the chance that more than that the cars carry more than 1,075 people is small. It's about 8%. So after this problem, you have a bunch of other problems to try, and then you arrive at control charts. And I'm going to ask you to watch the videos on control charts because it's just a rudimentary exercise. It's not hard. Once you learn how to do it, it's not challenging. Okay, so just review that, learn how to do that. And that's it. So we have covered half of this formula sheet already. And we still have, well, we have a little bit of time. I can begin inference. I'm going to start with inference. I'll do about 15 minutes, 20 minutes of inference. Do you have any questions for me right now? So I know I ask a lot that you keep up with what I'm doing. All the things I talk about are in the notes, so you can review them again on your own if you haven't already. Plus you get the video to watch. Does anybody need me to go back? So I'm going to open up the inference notes. Oops, that's not what I wanted to do. So I talk a lot. This is the largest data set, module or unit. Lots of pages here, 75 pages. Lots of problems and answers. So that's why it's such a big unit. I'm going to start on page, what is this on here? It says page 4. I'm going to start here. So we're going to talk about inference. We're going to use the theory that we've built up regarding sampling distributions of sample statistics. And rather than answering questions about what outcomes we expect in the sample, we're going to use those expectations and reverse things. Instead of looking at anticipating the results of a sample, we're going to actually draw a sample, get some results from the sample, and then talk about what it tells us about the actual parameter. So what does the sample statistic tell us about the actual parameter that we might not know, okay? So that if we don't know it, what does the sample statistic tell us about it? So this is different. What we were doing till now is I give you the parameters and you tell me about the sample results. Now I'm going to use the sample results to talk about the parameters and what I think they should be. So here's an example. In a study with a new vaccine involving 53 lung cancer patients, 29 survived 5 years after surgery. So that is our data. This is our statistic. 29 survived. This is our success. This is our X. Okay? X, where this is a binomial distribution looking for successes in 53 trials. Now, from this sample, this result, this study, we found that it's 29, or we could compute that as 29 out of 53. What percentage would that be? So I'm going to use 4 decimal places when I work with proportions, okay? That's one other trick that you need to know to get my answers. Although the options here have 2. I stick with 4 decimal places, usually. So this is the sample proportion. More than half of them survived. So this gives me an estimate of the survival rate, okay, the chance of survival. However, that's not sufficient when I know something about p hat. What do I know about p hat? I know that that p hat is just one of many I could have had. This was my sample, but from the population I could have had a different sample. From the theory, I know in number 2 that p hat has a mean p and a standard deviation p 1 minus p over n square root, and is approximately normally distributed in certain circumstances. So really p hat comes from a whole distribution. So why don't I present p hat with an interval of a range of values? Because I have a whole distribution related to p hat that I know what the pattern of the distribution is. Why don't I use it to give an answer? To summarize my results or summarize my study, conclude or report on my research. So what I'm going to do is use that fact that I know we can check n times p, but I don't know p, so I'm not going to check that. So I'm going to assume that p hat is approximately normally distributed. And what I'm going to do is say I want to create an interval that's 98% of the observations around p hat. Now if you have a normal or standard normal distribution, right, because p hat is approximately normally distributed with a mean p and a standard deviation p 1 minus p over n square root, then looking at the standard normal version, what I want to do is I want to create an interval that is so many standard deviations from p hat. So you know how we do this? Usually we go x bar plus or minus, 2 standard deviations, right? I want to do something like that. I want to make an interval. But the interval I'm going to choose is not going to be determined by 1, 2, or 3 standard deviations. It's going to be determined by how many observations it captures around the mean. So what would be the limits? How many standard deviations away do I need to be to have 98% in the middle? How do I figure that out? Okay, so for 98, if it's 98 in the middle, then it should be 2% out here and 2% out here. So what would put 2% in the tails? I need to check. Let me fix that. It looks so messy. So what would put 2% in the tails? I would need to go to the table and see, I'll write this 0.0200. How many standard deviations below the mean would I find that to the left? So let's go to the tables. And I'm looking inside the table for 2%. And the one that's closest is this one. So it's negative 2.05. Right? That's the closest to 2%. Negative 2.05. So this is negative 2.05 and this is positive 2.05. So it's not two standard deviations. To be more precise, it's going to be, to get 98% in the middle, which is being requested here, level of confidence, I need to be 2.05 standard deviations away. Okay, so what are the standard deviations? Well, from the theory, I also have the standard deviations. I have this here, but I don't know P. So in every case, I don't know P, but I'm going to estimate P with the best guess I have from the sample. So let's say I don't know what the true proportion is. I'm taking that away from you. And I don't know, well, this one and this one, I don't know what any of these things are. But from my sample, I've got P hat, and I'm going to run with it. I'm going to use P hat as the true proportion, and the standard deviation, I will use the P hat that I calculated as well. So I'm going to put P hat 1 minus P hat over n square root as the standard deviation. So what we have here is called a confidence interval. This is the point estimate, the best guess, your unbiased estimate for P, the true proportion. This is called the critical value. It's how many standard deviations away you need to be to capture a certain percentage known as the confidence level, certain percentage of the observations given the theory. And then I need to multiply by standard deviations, but we give this a special name because we have put an estimate inside of our estimate. Like we're trying to estimate the standard deviation, we use an estimate inside. So we actually have the different name for this. We don't call it is the standard deviation, yes, of P hat, but we call it the standard error. It's the standard deviation. Right? So this is a confidence interval. This is the confidence interval for the true proportion based on the sample results. So you need to find out which one of these it is by making the calculations. So can you guys do that and tell me which one it is? Which one is the closest? So they all have the same p hat. So the only difference is going to be this one. So we already figured this was 2.05. These have 3 digits, and I'll explain where that comes from tomorrow. So 2.05, I guess these ones are closest. So I just need to solve. What's the difference between these two? Not sure what happened there. Okay, let's get the let me double check my selection for 2%. Oh, that's why. Nobody saw what I did. I'm so sorry. It's not 2%, that's why. I don't know why I have 2 of the same option. It's 1% on each side. Oh, I wish I could delete that from the video. So it should be 1% on each side, not 2. So 1% on each side. Let's do that again. Then I can fix this. Not 2% on each side. So we gotta look up 1%. Anyway, I get to do it again. So I'm looking for 1%, 0.0100, and the best option is, this is the closest, negative 2.33. Negative 2.33. Sorry about that. So this is negative 2.33. And this is positive 2.33. And then I never noticed before that these two options are identical. But okay. This is now 2.33 standard deviations away. And I have p hat. All I need to do is get so that's going to be the standard error. So you end up with 0.0684. So this is the standard error. It's the estimate of the sample proportion. I actually have to put a hat on the sigma too, so that looks really confusing. That's why I don't do it. I'll just leave it out because it's an estimate with an estimate inside. So the answer, the best answer is B. So I apologize about having the 2 instead of the 1%, but it forced us to do it again. All right, so what we've done so far is I've shown you an example of computing a confidence interval for the true proportion as determined by the sample result. So what we've just done is used this. Actually, this whole column, this is the formula for the confidence interval, and this is particularly for inference on the proportion without knowing P, of course. So you use P hat from the sample as a substitute or your best estimate of P and create an interval. The interval, the format is always, in general, critical value, not critical value, point estimate plus or minus critical value times the standard error. And that will create an interval similar to x bar plus or minus 2s or 3s that demonstrates a C level of confidence that you capture a certain proportion of the observations. So tomorrow we are going to finish this row with inference on P where P is not known, and finish this row, get through the 5th row, and then I will hint at the 6th row so you can just study everything and be ready for the test. So tomorrow I'm going to aim to finish everything. There might be a few things outstanding, but I want you to just work ahead if you can. If not, if you're stuck somewhere, please let me know and I will clear it up tomorrow, because tomorrow's Thursday and it's our second last class. Okay, so keep me posted on your progress. I am available if you have questions. The test, the last test will be on the weekend, and then your final exam will be on Monday. There is a document in Unit 6 for inference. There are 2 things to look at. One is the mock final exam, which is a sample exam. And I also have a document called Approximate Final Exam Distribution, where you see the layout of the coverage, the topics covered in the final exam. And the final exam is 40% on inference and 60% on the other stuff. And half of that, more than half of that, is going to be on the units of 4 and 5. Okay, but obviously you use a lot of Unit 2 NOR to do all these problems, so you still need to have that knowledge. Okay, so the test will include everything up to what we do tomorrow, I guess. Will be on the test, and the final will include everything. Okay, so we'll talk more about it tomorrow. I'm going to let you go for now, and please keep me posted on any issues that you're having with studying, and I really apologize for messing up I should put a note in the description that I messed up that the problem here with the 1%. I'll put that in the description so maybe save people some trouble. Okay, any questions? Otherwise, say have a good night. My pleasure.